Alright, we are back learning about free body diagrams today, which basically show the force vectors on an object. If we look at this picture, this is an example of a free body diagram. And basically it just shows not only the magnitude or the size of the force, but also the direction of all the forces acting on an object. To get used to some of the types of forces, this is the force of friction, this is the normal force, this is the applied force, and this is the force of gravity. In this case, all the forces look to be about the same magnitude, just different directions. So if they were indeed the same, then it would be in equilibrium because all the forces would cancel out. There are quite a few different types of forces that we're used to. One is weight, and we know that weight, which could be symbolized with a W, is also the same as the force of gravity, so something to consider. We know that the normal force is often the force pushing up on an object, or the support force, so that's F sub n. Friction, we know, is often opposing motion, so for example, the force of friction would look like this, F sub F. An applied force is either a push or pull. In this case, maybe the applied force is going this way, and we put it as FAPP. A spring force would be something like anything that has to do with a spring, like the shocks on a car or whatever. So something like that could be F, but sub S. Springs we don't use too often, but then the force of tension could be like a rope or something like that. Say that you were doing pull-ups, maybe each arm was hanging, then you could have a force of tension, which would be F sub T for each of them. Either way, as we get more practice with these free body diagrams, we'll get much more comfortable and confident with the types of forces. In order to draw a free body diagram, we have to look at one specific object. When we do that, we're going to draw a box to represent that object. It doesn't have to be pretty, and if it's a car, for example, you don't have to draw a car, just a box will do. And then you're going to draw an arrow or a vector for each force acting on the object. And then you want to make sure that the arrow not only shows the direction, but the relative size of the force. So what we've been doing, and you've seen examples of, is maybe like a textbook on the table. Well, the textbook on the table has a weight, which is the force of gravity, and then also there's a normal force, or the force pushing up on the table. This up and down forces are opposite, right? But their magnitude or their size should be about the same since the book isn't moving. But we'll get into that more. This is an example of a free body diagram, similar to what I just drew on the previous couple of slides. But this has 4 forces acting on it. That doesn't always have to be so, but in this case it is for an example. Let's do a few problems to try it out. If we have a book that's at rest on a table, let's diagram the forces acting on the book. Think about it. There would be the weight of the book, or the force of gravity, and then of course the normal force from the table pushing back up. Let's take a look at the answer. Here's the answer with the normal force pushing up and the force of gravity pushing down. That would be your free body diagram. Notice that there's no horizontal or left and right forces, just up and down in this case. And that's okay. Only 2 forces acting on it is fine if that's really only the forces acting on it. Let's take another example of an egg that's free falling from a nest. Think about it. If we ignore air resistance and an object is free falling, what's acting on it? The only thing that's acting on it is really the force of gravity. Nothing else. Let's take a look at the answer and see. You can see from the picture that we were correct. The force is definitely unbalanced because only one direction does there a force. So if there's an F net, right, a net force in the downward direction, that means that we must be accelerating downward as well, which makes sense. As objects drop, they accelerate when they're in free fall. Don't forget that whole relationship between net force and acceleration is because of Newton's second law. In this third problem, we have a flying squirrel gliding. We're not flapping wings, just gliding through the air from a tree to the ground at a constant velocity. Constant velocity is important to remember because when you have constant velocity, what does that say about acceleration? Constant velocity means that there is no acceleration. Keep that in mind. Let's think about it though. If a flying squirrel is gliding through the air, there's definitely the force of gravity. And if it does say to consider air resistance, I imagine air resistance is pushing up on the object. Now, since there's constant velocity, no acceleration, that means that no acceleration, there must be a net force overall that equals 0. So that means the up and down forces must be equaled out. Let's check out the answer. Should equal 0. We will correct. Force of air resistance is up, force of gravity is down, but the two magnitudes of the vectors are equal. And that makes sense because net force should equal 0. Why? Because if it's a constant velocity, that means that there should be no acceleration whatsoever. Let's take a look at problem 4. A rightward force is applied to a book. So here's a book, and to the right a force is applied. Fair enough. Consider the frictional forces. Alright, if the direction of the book's going this way, then friction must be going the opposite direction. We know that frictional force always opposes motion. We also know that if there's a book and it's on a table, there must be a force of gravity pushing down, and the table is pushing up by just as much. So there's a normal force as well. Let's take a look and see if we got that one right. We did in fact get it right, though it didn't say if it was moving at a constant velocity or accelerating, but in this case, since the applied force is greater than the frictional force, the overall net force is towards the right, which means that the acceleration is towards the right as well. Problem 6 is a car running out of gas and coasting down a hill. If that's the case, let's think about it. A car coasting down the hill is really just affected by, what, the force of gravity? Is there anything else? Sure. If it's coasting down a hill, there's still friction opposing its motion. So there's a frictional force. Is there a normal force pushing back up on the car? Definitely. But there's definitely no applied force. So let's see if we got that right or close to it. So we did all right with this one. Friction definitely opposed the motion, even though it was still going down the hill. Gravity's pulling the car down, and of course the earth or the ground is pushing back up so that the car can be supported. If we want to recap about net force, right, the idea here is that if all forces cancel out, the net force is equal to 0. That's when they're all balanced. Remember, if net force is 0, that means that acceleration is 0, which means that the object is either moving with a constant velocity or not moving at all, so v would equal 0. An unbalanced force exists when either the vertical or horizontal forces don't cancel each other out. In that case, there's a net force that is greater than 1, in either direction, of course, but greater than 1 in magnitude. So that means that there must be some kind of acceleration, according to Newton's second law, right? Because if there is a net force, there must be an acceleration in that direction. Newton's second law states that, and F equals ma. Looking at the net force here, there's an upward 1200 and a downward 800. That results in a net force of upward of 400 newtons. This one has an upward and downward force of 50, so those cancel out. You're left with just a frictional force, which gives you a net force of 20 newtons. If we want to look at it a different way, two forces in the same direction add up to give you 10. If they're in opposite direction, they cancel out to give you 0. What if they're two different ones? Just add them up within their same direction and they give you 15. What if you have 5 forward and negative 10 backwards? You end up overall with negative 5 backwards. 5 forwards plus negative 15 backwards gives you a negative 10 overall. And then just not horizontal, but up and down. If it's 10 up and negative 5 or 5 down, you end up with a net force of 5 up. And remember, wherever the net force is, whatever direction, that's the direction acceleration is in. Let's look at and think about net forces from this. This object is definitely accelerating. If acceleration is happening, then there is a net force overall. This one, we're at a constant v. If we're at a constant velocity on this one, then acceleration equals 0. which means F net, the overall net force as well, equals 0. This one, you are slowing down. So if that's the case, your acceleration is in this direction, your velocity is in this direction, and since you are accelerating, you do have a net force overall. If we want to do a recap with graphs, if you are a constant velocity, that means your acceleration equals 0. So that means in this case, your overall net force equals 0. If your velocity is changing, so you're slowing down, then you do have acceleration. And if you do have acceleration, then you do have an overall net force. And in this case, if velocity is increasing, you do have acceleration because you're speeding up. So that means you do have an overall net force as well. So that's going to conclude our talk about free body diagrams. And the more practice you get, the more used to it you'll get. But just remember, Newton's first and second laws overlap very well with this. So everything becomes one big pot of information. So keep on cruising. Thanks for listening. Best of luck.